Hello everyone, my name is Yuri Zholodov and I am from Kharkiv University of Radio Electronics. It is my great pleasure to give a talk 9,10-diphenyl anthracene polyvinyl butyral glassy carbon-based transducer from spin coater development to electrochemiluminescent applications. Electro-generated chemiluminescence, or ECL, is a phenomenon which is a method of electroanalytical chemistry which is widely used for environmental and biomedical assays. On the left you can see the basic scheme of ECL reaction, which is commonly used worldwide, and on the right there is a clinical ECL analyzer example from Hoffman-LaRoche. It is Alexis 2010. Among the basic current directions and trends in the ECL research, it is the search of new detection techniques and new ECL systems. Previously in our research we have developed and demonstrated a new ECL correctant, sodium tetraphenyl borate. It is quite efficient system, but at the same time it has some disadvantages comparing to commonly used ones like tripropylamine. For example, when it cannot be efficiently used with commonly used fluorophores like ruthenium trisbipyridyl complex that was shown on previous slide as an example of ECL reaction, because it creates a precipitate with it and gives some background emission from the Ruby P itself. In order to solve such problems, if you want to apply such new correctant as TPB, tetraphenyl borate, then it is necessary, it is possible to use a different approach when a fluorophore, which is non-ionic and not water soluble, is incorporated into polymer film on the electrode surface. For example, previously we have demonstrated the use of Langmuir-Blodgett technique for deposition of ordered monomolecular films on the electrode surface with the incorporation of some fluorophores and ECL from such systems. But the problem is that the technique is quite laborious, it's very slow, and the commercial equipment for deposition is quite expensive, starting with $5,000 and above. A good alternative for such complicated techniques is a very commonly used method of spin coating for deposition of thin polymer or organic films. The method does not give such comprehensive ability to deposit single molecular layers or bimolecular layers, but at the same time it is very simple and cheap, and a lot of equipment for spin coating exists. At the same time, depending on the features of such commercial equipment, the price tag can also be quite high, reaching up to some dozen of thousands of US dollars. So our goal, one of the goals of this work, part of this research, was to develop a simple, cheap spin coating system which can be used for deposition of polymer films on the electrode surface and creation of such films. So when we talk about spin coating, the method is actually based on rotating electrode or substrate surface, which is spinning, and deposition or drop casting of some solution containing required mixture of polymer, fluorophore, some other species. The solution is made in organic solvent which evaporates, and when this happens, when evaporation happens during the spinning, the uniform film is formed, as you can see on the steps 1, 2, 3, 4 on the picture, on the right picture. So our home designed spin coater was actually based on simple cheap components which are easily available. The spinning mechanism was taken from the hard disk drive. It is using a brushless DC motor to drive the rotation. The basic control of the system was made using the Arduino system, Arduino Mega 2560 CPU. The display of spinning rate is given with the LCD, and the control of the spinning rate is made with two buttons to increase or decrease the spinning rate. So the overall price tag of this device was less than $25. So here you can briefly see the basic components and their approximate price. So the total cost is about $25. So for testing this home design spin coater, an ECL system was made. So there was used an electrode, a glassy carbon disc electrode on the left top picture. In order to fix it on the spinning plate of a spin coater, a special adapter, which is not shown here, was fabricated. The electrode was covered with a polymer film made of polyvinyl butyral polymer as a matrix, and it was impregnated or doped with fluorophore 910 diphenylanthracene, or DPA. Its optical spectroscopic properties are shown on the left bottom picture. So it is a blue emitting fluorophore, which is very efficient. It has efficiency of fluorescence up to 100%. At the same time, it is well known for ECL research in non-aqueous systems. So after deposition of such film on the electrode surface, on the glassy carbon disc electrode, the electrode was placed in a conventional 3-electrode ECL cell, and cyclic voltammetric potential scans were applied to the electrode. So potential was linearly increasing from 0 to some maximum voltage. Here on this slide it is 2 volts, up to 2 volts, and then reverse back to the 0 at a scan rate of 100 millivolts per second. During this process, it is clearly seen that the film that is created is semi-permeable. So despite of the fact that polyvinyl butyral PVB is actually non-conductive material, the thickness of the film under conditions which were used is such that electrochemistry is clearly seen. So the current through the film is present, electrochemical current, oxidation of co-reactant is happening, and at potentials of 1.25 volts and also at high potential of about 1.7, a clearly observable 2 peaks of ECL emission red curve is seen during electrochemical process, the ECL from such films. In general, the presence of 2 ECL emission peaks is not so common in ECL research. To understand the problem, in order to try to understand why it is happening, we can look at what is known about correction mechanism of ECL with tetraphenyl borate, TPB. And previously it was already reported the existence of 2 waves of ECL with another fluorophore, rubran, which is related to single oxidized species of fluorophore, the cation, and dication, twice oxidized species. In order to prove that, to check that both waves have emission originating from the same emitting state, spectroscopic studies were done. First of all, using a set of optical glass filters, it was measured the emission from first and second peak, during first and second peak of ECL. On the right picture, such spectroscopic data is present. You can see clearly the first and second peak, red and black. They have the same structure, so they mean the emission state is the same, the amplitude is different. At the same time, if you compare this data with fluorescent spectra of diphenylanthracene, a clear shift of the wavelength, a red shift, is visible. But still we are sure that diphenylanthracene is the emitting state, since there is no other emitters in the system. On the left slide, you can see the same ECL emission, which is recorded through the blue filter at the wavelength of 425 nanometers, and in the inset there is a non-filtered emission, so you can see the amplitudes and the ratio is absolutely the same, so the emitter is actually the same for both waves, first ECL wave and the second ECL wave. When we talk about ECL on a spin-coated films, the film's properties or film deposition parameters are the main factors that determine how the phenomena is working, how the transducers for analytical applications will perform. The main parameter that is affecting is the thickness of the film. This determines how permeable it is for electrochemical processes, for the current flow, for the molecules to be transferred from the solution to the electrode surface to be oxidized there and go back. So on the left picture you can see the dependence of ECL intensity for such films versus the dilution level of the polymer. By changing dilution ratio with the solvent during the deposition process, the thickness of the films is changing. And here it is given as percentage of stock solution of dilution, and it is clearly seen that there is a distinct maximum of ECL emission present. At less diluted films, the density of film is too high, so it's not really permeable for electrochemical process. When the film is too diluted, probably the reason is that there is not enough active species, not enough fluorophore to participate in ECL reaction, so that's why the ECL decreases. So there is clear optima, which was the parameters of this optimum were used for ECL studies in future. Also, the content of fluorophore per matrix molecules of PVB is also important, and on the right picture it is clearly seen that the increase of concentration of diphenylanthracene in the polymer from 1 to 5% gives a very strong increase of 2 peaks of ECL, but at different slope. They have different slope. The first peak increases more drastically, especially taking into account that the ECL intensity is given in logarithmic scale. When talking about ECL properties of the films made by spin coating, here it is clearly seen that another parameter affecting the emission, ECL emission intensity, is the scan rate, potential scan rate. When it is increasing, the first and second peak intensity increases, but first peak increases much faster with the increase of scan rate. The second peak is increasing but has a kind of saturation here. That gives us idea that the fastest scan rate should be used, or instead of using the cyclic voltammetry, we can actually use the pulsed electrolysis, which will give the highest ECL intensity. So we did check this idea, and it does really work according to this idea. So when the pulsed electrolysis is used, the ECL intensity is extremely high. It overwhelms the cyclic voltammetry results many times. On the left picture, a pulsed ECL response, the red curve, is shown. Also, it was found that stability of such films is not perfect. So if you look at the inset, the 3 consecutive pulses are given, the ECL intensity decreases from pulse to pulse. So due to this high intensity in the pulse mode, it is possible to have very, very sensitive detection of our TPB correctant, tetraphenylborate correctant, using this film's modified electrode. It was found that the peak intensity is not so stable between the pulses, while the integral of light emission, which is given on the left image, black curve, is much more stable. So that's why for measuring the capabilities of detecting correctant the integral value of light emission during the pulse was used. On the right picture, you can see the dependence of this pulse integral intensity versus the concentration of correctant. And the correctant concentration on this slide is given from less than 1 nanomole and up to 1 micromole. So the system is extremely sensitive for TPB detection. So it is possible to conclude that, first of all, the home designed spin coating system, which can be done very simply and cheaply, is working well. It allows to deposit very nice spin coated films. And the second thing is those spin coated films consisting of polymer with fluorophore like diphenyl anthracene, polycyclic aromatic hydrocarbon, gives very efficient ECL emission in aqueous solutions and can work for detection of correctants like TPB correctant, and potentially some other correctants can be used. Also, according to what is known from previous studies of this correctant, its ECL efficiency can be affected by the presence of some oxidizers or oxidants in the solution. So the method can be used, and these transducers, modified electrode transducers, can be used for detection of such species by indirect influence on the ECL efficiency of the correctant. So further work in this direction will be focused on optimizing the deposition technique of the film parameters, the content of the film, try to use other polymers and fluorescent species, and possibility to find other good applications for detection of useful, important, especially biomedical important analytes. So, and finally, I would like to say thank you for the support of this research from the Ministry of Education and Science of Ukraine, state projects and project for young scientists, as well as support from Chinese funding organizations, from the National Natural Science Foundation of China, and also from the program of the President's International Fellowship Initiatives for Visiting Scientists in China. Thank you for your attention.